Hello, my name is Pierce Christie and welcome to my DSP video assignment. In this assignment we are required to make a recording of ourselves speaking our name and then import that signal into MATLAB and to play it back. So as you can see here, I have the code to do that.
This is Pierce Christie.
You just heard there the audio signal that I imported. So I imported that audio signal using the audio read function. The audio read function stores the value for FS, and you can see in this case FS was 48,000. I used this line to change the audio signal from a double to a single, and then used the sound function to sound the audio file that you just heard. We were then required to plot this signal in the time domain. So you can see this plot here, time in seconds is the x-axis, amplitude is the y-axis, and you can see what the speech signal looks like in the time domain. You can see it's approximately 3 seconds long. To do this, we created a time vector from 0 up to the length of the signal, -1, all divided by fs. I used the plot function to plot t, being our time vector, versus the signal. And I used the y label and x label to add the x and y labels to the graph, or to the plot. We then had to run a line of code to get the tone frequency and the noise cutoff frequency. This was given in the Word document. Next, we were required to synthesize high frequency noise and a tone and add these to the speech signal. So to synthesize the high frequency noise, we created a random signal the same length as my voice signal. Then, using a butter filter, I created a high pass filter that filtered out all the low frequency noise and kept all of the high frequency noise. And then I passed the random noise signal through this filter and was left with just high frequency noise. And then to create the tone, we used one of the frequency values, the tone frequency given to us from the previous line of code we ran, and we used that with the sinusoid formula to create a sinusoid tone at this particular frequency. Then we added all those together, so we added the original voice signal, the high frequency noise and the tone together, and we added it together in a new signal called sig. Next, we had to design a second order filter using MATLAB's butter function with a cutoff frequency set equal to half of the noise cutoff frequency. So to do this, we used the butter function, specified the order as 2, and then specified the cutoff frequency to be the noise cutoff frequency divided by 2. And this returns B and A coefficients for that filter. As you can see here, B coefficients were found to be 0.1868, 0.3737, and 0.1868, and the A coefficients were found to be 1, negative 0.4622, and 0.2096. We were next required to draw a signal flow diagram and write out the difference equation of the system we designed. So as you can see here, here's the signal flow diagram. You can see the B coefficients relate to the X event terms and the A coefficients relate to the Y terms. The sign on the X terms remained the same as the B coefficients, but the sign on the Y terms has a sign change involved. So that went from being negative 0.4622 to positive 0.4622, and from being positive 0.02096, it went to being negative 0.2096. Using the signal flow diagram, we then created the difference equation as shown, and then from there the next step from there, we had to calculate by hand the first 3 outputs of the system if the combined signal was applied. Using MATLAB, we found the first 3 values of the combined signal to be 0.0998, 0.0972, and 0.0654. And using our difference equation, we were able to calculate that the first 3 outputs expected were 0.01864, 0.06407, and 0.0929. We can confirm that this was the case. And you can see here we got 0.0 187, 0.0636 and 0.0953 to be our outputs. These are a small bit different to the ones we calculated by hand, but that was just because of rounding error. We next had to design a minimum order filter which would reduce the high frequency noise by at least 60 dBs with a maximum of 3 dB ripple allowed in the passband. So you can see here, to find the minimum order we used the but_ord function. And this gives us the order and frequency we should use. So next we use the butter function with the order and frequency just calculated, and this lets us design a filter that matches the specifications required. We next had to design a second filter using MATLAB's functions to reduce the tone by at least 40 dBs and ensure the system was stable. So you can see here we used a fourth order butter function. And to make sure that this filter we designed was stable, we used the z-plane function. And you can see that the poles and zeros for this function all lie within the unit circle. But originally we had it set to 10, the order to be 10, and the poles and zeros were located outside of the unit circle, and that makes the system unstable. We can see here that if you remember the requirements, it had to have at least 60 dBs of attenuation for the high frequency noise. And if we look at this plot, this is the noise cutoff. Sorry, this is the tone frequency. Oh, apologies. Sorry, this is where we checking that we had to reduce the tone by at least 40 dBs, not the high frequency. So if you see here, this is the noise frequency. We'd expect it to be. Oops, apologies. We'd expect that frequency to be attenuated by at least 40 dBs at 0.1050 on the normalized spectrum. To check if this was the case, we used the freq z function. I'm sorry, I'm just making this a bit bigger so we can see it. Here we are. So if you remember, we'd expected to have at least 40 dBs of attenuation centered at 1050 on the normalized frequency spectrum. Oops, sorry, this is a bit slow. Apologies, I'll just set this again. And if we see here, there is a maximum of 80 dBs of attenuation, so there is at least 40 dBs of attenuation, and we can see it's at the frequency we wanted at 1050. If we now apply both filters to the combined signal and plot the magnitude frequency content of the input and output in hertz and label the axes, we should be able to see the effect that these two filters had on our noise. Yeah, so you see here, I'm just going to make this a little bigger. So if you bear with me, this is our tone frequency, and we can see the tone frequency has been massively attenuated. And if we zoom in here, you can see all that high frequency noise, and we can see that all that high frequency noise at the right hand side of the screen here, this has all been attenuated in the output, and you can see in the red the speech signal gets through with minimal attenuation, pretty much no attenuation. To do this, we just passed the output of one filter in as the input to the next filter. So as you can see that here. To plot the frequency axis, we created We use this line of code, so 0 to the length of the signal minus 1, and we divided it by the length of the signal multiplied by fs, and that gave frequency in hertz. Next, we have to identify a low frequency component that will produce a significant phase shift in the first filter, at least pi over 4 radians, and pass a sinusoid of that frequency through the filter, and verify that the phase of the tone has been altered by the expected amount. So here what we'd expect is, if we were to plot both the input and the output, what we're hoping to get is 2 sinusoids, and one of them we want to be shifted by 1/8 of a cycle. So to do this, we had to create the tone, which we have here. Then we wanted to filter the tone, then plot that original tone, and then plot the tone after it was passed through the filter. So what we're looking for here, as I make this bigger, is the phase shift. We want to see the phase shift of this filter. So if I make this full screen, so as you can see here, the output has indeed been phase shifted about 1/8 of a cycle. So that is everything. Thank you very much for watching.